Welcome back to the RISC-V assembly language module. We are going to talk a little bit more about the elements of the architecture. So, just to recap, instruction set for a particular architecture is a set of instructions that architecture can execute. It is represented by its assembly language. Instruction set architecture is an old concept. It dates back to the first electronic computers discussed in this paper by Burks, Goldstein and von Neumann, dated 1947 roughly. The key thing here is that each line of assembly code represents one instruction for the computer, and computer is going to execute that. The first element of the architecture are its registers. Unlike higher level languages like C or Java, there are no variables in assembly. They would be really complicated to implement in software, so assembly operands, those that follow the verb, are generally registers. What are registers? Well, those are hardware objects that sit inside of a processor core, and there is a limited number of them. Operations are performed on the data that is sitting inside the registers. The benefit is, since they're really local to the processor core and to the units that are doing the calculations inside the cores, they're really fast. They're lightning fast. What does that mean? If a processor runs at 4 GHz, that means every quarter of a nanosecond it can access its registers once per cycle. One cycle in a 4 GHz processor is quarter of a nanosecond. How fast is quarter of a nanosecond? Well, it's very fast. If you recall, the speed of light is 3 times 10 to the 8 meters per second. That means the light travels about 30 centimeters in a nanosecond, or about 10 centimeters, this much as 10 centimeters in 0.3 nanoseconds. That also tells us that if we put objects farther away than this far, there is no hope that we can access them as fast as we can access the registers. We can't beat the speed of light. So let's see a model of how does a computer look like. This is a picture that shows a level of abstraction of the operation of a compute system. Generally, a processor is connected to the memory, and in this case it is connected to the input and output devices. In this model, it looks like the input and output devices are connected to the memory. In real life, processor is the one that orchestrates loading memory from the I/O devices and sending the data from the memory to the outputs. Inside the processor, there is generally a control unit and a data path. Inside the data path, the main elements are those registers and the execution unit, typically called the arithmetic logic unit. The processor communicates to the memory by issuing addresses and reading data from the memory or writing the data to the memory. There is another important concept here. We don't want to accidentally write into the memory. We can read without any harm to the memory. We'll not alter the values when we read from the memory. But when we want to write to the memory, we need to say that we are sure that we really want to write to the memory. We do that by asserting this enable signal. And that is it. We'll really be working on this conceptual view of a computing system, of a processor, memory, and I/O, and we'll add a few elements to this class. But this is pretty good to start with. Remember, another view of why registers are important. Remember our other view of the abstraction of a memory system and principle of locality and memory hierarchy. The goal of all these memory systems is to make memory appear infinitely fast and infinitely large. Well, not that infinitely fast, extremely fast, like registers. But since we have a very small number of registers, we would like to make a lot of the bulk memory look to be as fast as the registers. How fast are the registers? Well, they're essentially, in this Jim Gray's analogy, as the data that we can keep in our head. So how many numbers can you keep in your brain? I mean, for me, that's kind of a limited number, maybe a dozen or two, and I can retrieve them in about a minute. We'll recall these equivalences of how long does it take us to retrieve the data for other types of systems. Important thing about the registers, since they are really deep in the hardware, right next to the execution cores, there has to be a limited number of them. We cannot have an infinite number of registers because they need to be close to the core. So all our assembly code needs to be carefully crafted to utilize these registers for fast execution. The number of registers is limited, and it is one of the main features of the instruction set architecture. Some instruction set architectures, like x86, have a very small number of registers. There are only 8 general purpose registers and then some specialized registers inside x86. RISC-V has 32 registers. How did we come up with 32? Well, it is based on a Goldilocks principle. Smaller is faster, but too small is bad. If you have too many of them, it's going to slow down the machine. Goldilocks principle says this porridge is too hot, this porridge is too cold, this porridge is just right. In RB32 variant of RISC-V, each register is 32 bits wide. These groups of 32 bits, as we mentioned, are called words in RB32. Each word is 4 bytes, 32 bits. The textbook uses 64-bit wide words. It is also a word, but it's a 64-bit word. So the width of a word is associated with a variant of the architecture. Let's dive a little bit more into the concept of registers. So there are 32 registers in RISC-V, and they're numbered from 0 to 31. We usually refer to them as physical registers, x0 to x31. x0, we'll talk about that one later, is very special because it is hardwired to 0. You cannot change its value. It always stores a 0 because we like to have a 0 handy, always around a representation of a 0, always near the processor. Now, registers will have their logical names. We're going to add them a bit later. A few other differences between the variables and the registers. In C and other higher level programming languages, variables need to be declared first and given a type. So we would like to distinguish integers from characters because it's kind of important to know that somebody should warn us if we try to add integers and characters. So we should make sure that that's actually what we want to do. More importantly, in C, we need to know how much memory is going to be taken by a particular data structure, and that very much depends on the data type that uses. So each variable can only represent that data type, otherwise we would have all kinds of memory errors. Registers in assembly have no type, and it's the operation that operates on them, that verb that operates on, that is inside the instruction, determines what we actually do with the contents of the registers. Hope this makes sense. It'll make much more sense when we see particular examples of that. One important note here is it's always good to have comments in your code. So use comments to make your code more readable. Hash is used for RISC-V comments. Anything to the left of the hash mark is your code. Anything to the right is ignored by the compiler and by the assembler, and is not sent down to the processor. There is difference from C that you cannot have multi-line comments like we had in a C / star, start the comment, / ends the comment. That does not exist in the assembly. This style of commenting has been around for a long time. Here's a good chunk of history. This is Paula's guidance computer, and you can find all of its code on the GitHub. It has been recently, about 2 years ago, has been put on the GitHub. The lead programmer was Margaret Hamilton, and you can see the printout of the code that I believe is for the lunar lander. That is taller than her. Done, I bet, on a line printer. And you will find hash marks and silly comments behind that, like temporary, I hope. All right, back to the assembly instructions to try to wrap it up for this short segment. In assembly language, each statement is called an instruction. It executes one of a short list of about 40-ish or so RISC-V instructions. Each line of assembly language contains at most one instruction. And these instructions can be viewed as, additions or subtractions or logical operations. But let's pause here, jump to the next video in a few minutes to see practical examples of how do they look like. See you there.